Hi everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of EC at IARE, Hyderabad. Yeah, today we will be discussing about filter design techniques using the filter like a digital filter. Basically, we know that a digital filter. Basically, we are having the two digital filter. One is IER and FIR filter. In this session, design of discrete time IAR, infinite impulse response filter from continuous time filters. So here, design of for discrete time IAR filters from continuous time filter. Here in this, the traditional approach to the design of the discrete time IAR filter involves so the transformation of the continuous time filter into a discrete filter meeting prescribed specifications here. So with this, after that we write to design of the discrete time infinite impulse response filter from continuous time filters. So the reason one for designing that one. So the art of the continuous time IAR filter design is highly advanced, and since useful results can be achieved, it is advantageous to use the design procedure already developed for the continuous time filter. So by using this major reason, the art of the continuous time infinite impulse response filter design is highly advanced. Based on this advanced level, we are to design our IER filter with continuous time IER filter design. Okay, next second reason, the many useful continuous time infinite impulse response design method have alternatively simple flows from the design formulas. Okay, therefore, uh, discrete time IER filter design methods based on what do you call such a standard continuous time design formulas are rather simple to carry out. With this, so the specific reason is involved here. The reason number three, so the standard approximation methods that works well for continuous time infinite impulse response filter do not lead to the simple closed form design formulas. So already we have discussed this all reason. By using this all particular reasons, directly we are able to design our concerned digital filter. So when these methods are applied directly to the discrete time infinite impulse response case, so steps of for the discrete time filter designed by transforming a prototype continuous time filter. With this, the specifications for the continuous time filter are obtained by a transformation of the specification for the desired discrete time filter. So find the system function of the continuous time filter. This is a way. After that, transform the continuous time filter to derive this system function of the discrete time system. With these 3 points, 3 steps of discrete time filter designed by what you call transforming the prototype continuous time filter. So constraints of the transformation. So based on these all constraints, easily we can analyze that all design aspects, how it is implemented, the steps, and so on. So to preserve the essential properties of the frequency response, the imaginary axis of the S plane is mapped onto the unit circle of the Z plane. It's one constraint. So with this, mathematically, where S equal to j omega, where Z equals e power j omega, here is or the real axis or imaginary axis. So how it is involved with the Z plane and S plane. After that, so second constraints is in order to preserve the properties of stability. If the continuous system has poles only in the left half of the S plane, then the discrete time filter must have poles only inside the unit circle. Okay, with this, the stability property, in order to preserve the properties of the stability, the continuous system has poles only on the left half of the S plane. You have to observe this on left half of the S plane. and then the discrete time filter must have folds only inside the unit circle. Okay, so steps of the discrete time filter design by transferring the prototype continuous time filter to obtain the specification of the continuous time filter by transforming the specifications for the desired discrete time filter. Find the system function of the continuous time filter. After that, they transform the continuous time filter to derive the system function of the discrete time filter, or we can consider it DTF, discrete time filter. So, transformation from the discrete to continuous. We have to observe this one, the transformation from the discrete to continuous. In the impulse invariance design procedure, the transformation is right to observe at, so where h into e power j omega is equal to hc of j into omega by td, where omega mod omega less than or equal to pi. Assume this aliasing involved in the transformation is neglected. The relationship of the transformation is, so where omega is equal to sigma is equal to what you call w by td. Okay, so steps of the discrete time filter designed by transferring the prototype continuous time filter, obtain the specifications of the continuous time filter by transferring the specifications of the DDTF, discrete desired discrete time filter. Okay, with this, find the system function of the continuous time filter. After that, transformation of the continuous time filter to derive the system function of the discrete time filter. Now coming to this continuous time in infinite impulse response filter. So here we have to use the tall filter. Popular filter is Butterworth filters. Okay, so using this particular filter, easily can analyze that a continuous time ER filter is suitable or fitted to this. After that, we go for Savishu type 1 filters. After that, Savishu type 2 filters. So after that, we will try to use that are elliptic filters and so on. Okay, infinite impulse response filter. This is all nothing but a digital filter. This is the major type of the digital filter, that is infinite impulse response, or we can consider the IER filter. So difference equation, we should follow this mathematical analysis. The difference equation is where y of n is equal to summation I is equal to 0 to where that I is equal to, where here it is, where I is equal to 0 to n ai x of n minus I plus the summation j equal to 1 to n bj y of n minus j, like this. So these are the difference equation. Coming to this transfer function, where h of z is equal to the summation I is equal to, where summation I is equal to 0 to n ai into z power minus I by 1 plus the summation j equal to 1 to n bj into z power minus j. But here we know that where n is order of the filter, where capital N is the filter's order, or where ai and bj, these two are ai and bj are the filter's coefficients. With this, using this all full filter coefficients and what you call order of the filter, you can analyze that transfer function. Okay. Next, IR filter have infinite duration impulse responses. Hence, they can match to analog filters, all of which generally have infinitely long impulse responses. With this, air filter have infinite duration impulse response will be analyzed. Okay, the basic techniques of the IR filter design transform well-known along analog filter into digital filters using complex valued mappings. This is the ideal IR filter infinite duration pulse response. How it is varies. Okay, the advantage of these techniques lies in the fact that both analog filters design, you can consider that AFD tables and the mappings are available extension in the literature. as per all digital filter techniques. We are concentrating only the IIR filter. This is the major advantage of the techniques lies in the fact that both analog filters design, tables and the mappings are available extensually in the as per the literature survey. The basic techniques are called the analog to digital filter transformation. However, the what you call AFD analog filter design tables are available only for low pass filter. You can consider other filters other than this low pass filter that AFD tables are not suitable. We also want design other frequency selective filters. So of that maybe we are using this high pass filter and band pass filter and band stop filter and so on. Because of that, AFT tables are available for only for low pass filter. We also want to design other frequency selective filters like high pass filter, band pass filter, band stop filter, band elimination filter, and so on. Okay, to do this, we need to apply frequency band transformations to low pass filters. After that, this transformation are also complex value. With this, so mapping and they are also available in this literature because of to design. Here, filter have infinite duration impulse responses, so it can be matched to the analog filters, all of which generally have infinitely long impulse responses. With this, so what are the design methodologies? Design methods. The following the analog to digital filter transformation methods are used in calculating the coefficients of infinite impulse response filter. You have to follow these popular methodologies. One is impulse invariant method. Second one is bilinear jet transform method. To achieve a digital filter that has certain specification equivalent to the analog filter, but we have no control over the phase characteristics of the infinite impulse response filter, or we can consider that digital filter. Hence, infinite impulse response filter designs will treat it as magnitude only. Okay, so hence magnitude designs. Okay, so now we have to use that first Butterworth filter. Yes, here this the frequency response by using the Butterworth filter. Okay, the magnitude frequency response of the Butterworth filter is ready to calculate by using this mathematical notation where h into e power omega square that is equal to 1 by 1 plus omega by omega c power 2 power n. With this, go on writing that what you call piece of code using this magnitude response, the magnitude frequency response Butterworth filter using the mathematical notation. Of that, we will try to verify that response, that omega versus sg of j omega, the frequency response of the Butterworth low pass filter is appeared. The time order of the filter is initially what you call n is equal to 2, where n is equal to 4 or n is equal to 8. What is the response with this? So what are based on the all properties? This will analyze that Butterworth filter design. Okay, Butterworth filter where hn of j omega square where at omega equal to 0 is also equal for all n. Hn j omega mod square mod at omega is equal to omega c is equal to 0.5 for all finite n order of the filter, where h of n e power j omega at omega equal to omega c equal to 1 by square root of 2 is equal to 0.707 into 20 log base 10 h and j omega at mod omega is equal to omega c is equal to what you call minus 3.01 decibels. Okay, using this all typical value where h of n, that h of n j omega square is a monotonically decreasing functions of for omega. Here, using according to this Butterworth filter responses, where hn j omega square approaches to ideal response as the value of n increases. Like here, this n is where n is equal to 2, n is equal to 4, n is equal to 5. So, go on increase the approach to ideal response as the value of n increases. The filter is said to be a normalized when cutoff frequency omega c is equal to 1 at radians per second. With this, the filter is from this normalized transfer function. So, a low pass filter and high pass filter, band pass filter, band stop filter can be obtained by suitable transformation to the normalized low pass filter specifications. Like this, we have to follow that Butterworth filter design while we are designing what we call IAR filter in person in the method. Okay. Here, go on expand this all mathematical analysis where Hn j omega square is equal to Hn of j omega into Hn minus j omega is equal to 1 by 1 plus omega by omega c whole power 2 power n. For normalized Butterworth low pass filter, omega c equal to 1. Right? Where here that using this s is equal to j omega, where since omega is equal to s by j, according to that, directly we are right to expand this hn of j omega, hn minus j omega is equal to 1 by this value, 1 by 1 plus what do you call where 1 by 1 plus omega 2 power n. Okay, so like this, try to interpret this one. The poles of are determined by equating the denominator to 0. Where this pole, where 1 plus, so 1 plus s by j by power 2 power n is equal to 0. If you want to calculate this, s is equal to minus 1 into 1 by 2, 2n into j. Okay, minus n here. This minus n can, this minus n can be written as what you call that what you call e power j pi of 2k plus 1, where k is equal to, right, to substitute k equal to 0, how it is affected, where k equal to 1, how it is affected the s value, and where k is equal to uh, 2, 3 and so on up to, and after that j equal to that e power j pi by 2. After that, we try to calculate that sk. That sk is equal to e power j pi of 2k plus 1 by 2n and to e power j pi by 2. Here also we are to substitute that k value, where k equal to 0, k equal to 1, k equal to 2, k equal to 3, and k equal to 4, and so on, 2n minus 1. Like this, the poles are placed on the unit circle with radius, what you call unity, and placed at angles, like here where s of sk is equal to 1 by what you call k pi by at an angle k pi by n, where k is ready to substitute k equal to 0, k equal to 1, k equal to 2, k equal to 3, 4, and so on, to n minus 1 when n is odd. If it is n is even, so go on substitute the 1 by at pi by 2, 2n plus k, what do you call k pi by n, where k is right to substitute k equal to 0, k equal to 1, where k equal to 2, where k equal to 3, where k equal to 4, and so on, to n minus 1 when n is even. Okay, like this. So we try to analyze this one. The poles are determined by equating the denominator to 0, or that we should follow that how it is reflected the minus 1. What the poles are replaced on the unit circle with radius unity and placed at angles. Like this, we have to observe this one where sk value is ready to measure, where sk is determined by using this. Poles are replaced on the unit circle with the radius unity and placed at angles. Okay, so now that n is equal to 1, where n is equal to 1 means where k equal to 0 and 1, that sk value, that sk is equal to 1 by at an angle k pi by n, where s0 equal to 1 by at 0, s1 is equal to 1 at an angle pi. Here it is, the poles lying on the left, the poles are lying at the left of of the s plane is what you call hn of s is equal to 1 by pi LHP, LHP, or s minus sk is equal to 1 by s minus s1 is equal to 1 by what you call 1 by s plus 1. So using this all poles of this particular figure, poles of the h1 of s is 2 of minus s, how easily can analyze that h1 of s and h1 of plus s, and in terms of s plane. Okay, like this you write to interpret. Okay, if this is related to n is equal to 1, by substituting n is equal to order of the filter is 1 with the time for the k values, where it is assigned. If n equal to 2, okay, that means here it is n equal to 2, since the k equal to 0, 1, 2, 3, where n is even. Okay, after that, we have to calculate that one sk value, where sk is equal to 1 at an angle pi by 2 pi plus k pi by n. In place of that s, the k value ready to substitute here, the k is equal to 0, what happens? Where k is equal to 1, how it is affected? Where k is equal to 2, how it is, where is that all s values? After that, we write to analyze the poles of the s2 of s, s2 of n, and so on. Where k equal to 3, if it is n is even. Based on that, we are to measure that s, that k equal to 0, whereas 0 equal to 1 at an angle pi by 4. Yes, if it is the k equal to 1, s1 is equal to 1 at 3 pi by 4, and so, and sk, where k equal to 2, s2 is equal to 1 at 5 pi by 4, sk, k equal to 3, that s3 is equal to 1 at 7 pi by 4. The poles lying on the left half of S plane is, using this all graphically, where what do you call, hn of S is equal to 1 by sigma, what do you call, LHP, S of S minus K is equal to 1 by S of S1 or S minus S2. Okay, S2 of S and S2 of minus S. You can observe this on a graphical representation for n is equal to 2. When you compare this, n is equal to 1 and n is equal to 2. Where here it is, especially this case is S1, S0 and S1 if it is n is equal to 1. Here n is equal to, where n is equal to 2, that k values are here, where initially that S0 explained, S1, S2 and S3, like this. So go on increasing the order of the filter n value. N is equal to 1 and n is equal to 2 and so on. How it is reflected based on the Butterworth filter. How it is digital filter is very variation. The poles lying on the left of the S plane, and the poles lying on the left half of the what do you call, below that one, by substituting these all values for measuring, for determining that SK. Okay, with this, okay, so S2 of S is equal to 1 by S plus 0.707 minus J 0.707, S plus 0.707 plus J into 0.707. So after simplifying this, 1 by S plus 0.707 whole square minus J 0.707 whole square is also equal to 1 by S square plus 20.707 S plus 0.707 whole square plus 0.707 whole square. After simplifying this, 1 by S square plus 1.1414 s plus 1. Okay, so like this we try to determine this is true of s. Like this, determine the poles of the low pass butterworth filter for n is equal to 3. Sketch the location of the poles on S plane and hence determine the normalized. This is the best example of this is the example, or we can consider this as the problem or maybe example. With this example, determine the poles of the low pass filter for n is order of the filter is 3. Sketch the location of the pole on the S plane and hence determine the normalized transfer function of the low pass filter. So coming to the solution, here where n is equal to 3, okay, according to this uh, problem. So here it is, n value is given where n is equal to 3, that means k equal to what do you call 0, 1, 2, 3, 4 and 5. Now based on this, that n is ready to decide, n is odd. But the next step, ready to calculate the sk. K we know from this, k value we know. So direct substitution for here. So sk, if the k equal to 0, okay, that means s0 equal to 1 at 0. Sk, if k equal to 1, we have to substitute k equal to 1. It is followed by s1 is equal to 1 by at pi by 3. Okay, k equal to 3. Okay, k equal to 2. S2 is equal to 1 at 2 pi by 3, where k equal to, here it is k equal to 3, okay, S3 is equal to 1 by 1 at a pi, okay, where k is equal to 4, that Sk is equal to what you call 1 at 4 pi by 3, where the k equal to 5, what you call S5 is equal to 1 by at 5 pi by 3. Like this, using this all value, try to analyze this graphical representation for this. Okay, so like this, here it is S0, isn't it? Where S0, S1, S2, S3, S4, and S5. Because of here it is K value substituted up to S0, S1, S2, S3, S4, and S5. Okay, like this, try to determine try to determine the poles of the low pass filter or low pass butterworth filter for n is equal to 3. Sketch the location of the poles on the S plane and hence it will normalize the transfer function of the what you call low pass filter with the SK. Okay. Now the poles lying on the left half of using this all the graphical notation. So we are interpret this. The poles lying on the left half of the S plane is, okay, so here it is h s of s is equal to 1 by pi s minus sk is equal to 1 by s of s2 of into s minus s of 3 into s minus s4. Okay, s3 of s is equal to 1 by s minus 0.5 plus j 0.866 s minus 1 s minus 0.5 minus j 0.866. Like this, we are ready to simplify this one. S3 of s is ready to determine. Okay, the poles are described on unit circle in the S plane. They are distributed off on the left of plane and off on the right of plane using the solid graphical notation. Okay, with this, okay, the normalized butterworth polynomials are observed here. So order of the filter is order of the filter followed by capital N using this butterworth polynomial. If it is n equal to 1, s plus 1. If capital N is equal to 2, s square plus, here it is s square plus square root of 2s plus 1, where n is equal to 3, s square plus s plus 1 into s plus 1. Okay, the order of the filter is 4, s square plus 0.76536 s plus 1 s square plus 1.84776 s plus 1 5. If order of the filter is 5, s plus 1 into s square plus 0.6180 s plus 1 into s square plus 1.6180 s plus 1. Like this, right, observe the distributed of the left half cycle based on this polynomials are observed. Next, design of low pass butterworth filter. How there is a possibility for designing the low pass butterworth filter. Previous approach is try to measure that S plane, how it is, where is that S plane, left of the S plane or right of the S plane and so on. Here N values, based on the N values, N value, order of the filter is 1, 2, 3, 4 and so on. Especially this design, the transfer function of the normalized Butterworth low pass filter is given by Hn of S is equal to 1 by, so pi S minus Sk is equal to 1 by Bn of S, where that Bn of S is the nth order normalized Butterworth polynomial. Just now we have verified the polynomial values. We have to consider this all polynomial. What are the what you call Butterworth polynomial? We have to analyze. We have to choose that all the filter. Okay. So where the low pass Butterworth filter has to meet the following the frequency domain specifications, where Kp less than or equal to 20 log Hj omega less than or equal to 0 for all omega less than or equal to omega p, 20 log base 10 h into j omega less than or equal to ks for all omega greater than or equal to omega s, where kp is, where in this that kp is equal to attenuation at the passband frequency, where omega p is equal to in decibels. If ks, where ks is attenuation at the stop band frequency, omega s is in decibels we have to measure. Okay, like this omega versus the gain in decibel 20 log hs what is of j omega. Like this we have to observe this on omega versus that kp value and the ks value, like this. So if using this all mathematical notation, easily analyze the graphical representation. Okay, the magnitude frequency response is like this. You have to verify this magnitude response and the what do you call omega is equal to omega peak and k equal to k to p. Like this, the 2n log omega p by omega s is equal to log 10 power minus kp by 10 minus 1 by 10 power minus ks by 10 minus 1. So easily trying to measure that all the order of the filter n is equal to log of 10 power minus kp by 10 by minus 1 by 10 power minus ks by 10 minus 1 whole power 2 log omega p by omega s. So where n is the order of the filter, the cutoff frequency omega c right to measure, where omega c cutoff frequency is equal to omega p by 10 power minus kp by 10 minus 1 whole power 1 by 2n, or where omega c is equal to omega s by that cutoff frequency omega c by omega s by 10 power minus ks by 10 minus 1 whole power 1 by 2n. Okay, like this the design of low pass filter and so on. Okay, now coming to this design analog Butterworth low pass filter to meet the following the specification. Okay, so where t is equal to 1 second. Okay, it is given that all where this is the given specifications. 0.707 is equal to less than or equal to h1 d power j omega less than or equal to 1 for 0 less than or equal to omega less than or equal to 0.3 pi h t power j omega less than or equal to 0.2 for 0.75 pi less than or equal to omega less than pi. This is the given values. So by using this all values, how we are calculating this order of the filter, what are the value, what are the given parameter and so on. And coming to the solution, passband edge frequency omega p is given is 0.3 pi radians per sample according to given specification. Stopband edge frequency omega s is equal to 0.75 pi radians per sample. Passband edge analog frequency omega p is equal to omega p by 1 is equal to 0.3 pi by 1 is equal to 0.3 pi radians per second. Now coming to the stopband edge analog frequency omega s, okay, is equal to omega s by 1 is equal to 0.75 pi by 1 is equal to 0.75 pi radians per second. But here we don't know that all kp value. So the kp value, right, to calculate that, where kp is equal to 20 log of 0.707, so is equal to 3.01 decibels, where ks is equal to 20 log 0.2 is equal to minus 13.97 decibels. The order of the filter is, you know that order of the filter is n. If you want to calculate by using this given problem or given example, where we have to follow this formula where n is equal to, n is the order of the filter, n is equal to log 10 power minus kp by kp, we know that one kp value, okay, kp by 10 minus 1 by 10 power minus ks by 10 minus 1 by whole power 2 into log omega p by omega s. Okay, it is also equal to that, what you call log 10 power 3.01 by 10 minus 1 by 10 power 13.97 by 10 minus 1 whole power 2 log of 0.3 pi by 0.75 pi. Okay, it's also equal to log, after simplifying this, log 1 by 24 by 2 into minus 0.398. After simplifying this, so right, to verify that all order of the filter is right, to observe that order of the filter is true. Okay, so here it is. So with this, that omega versus the sigma versus 20 log, what you call hs of j omega, graphically the low pass filter. Okay, Butterworth low unlock Butterworth low pass filter. Okay, specifications is right to observe here graphically. Like this, we are to determine unlock Butterworth low pass filter to meet the particular specifications where t is equal to 1 second. Okay, with this, or we can consider this. This is the one way. Now they are calculating or determining the unlock Butterworth low pass filter to meet the particular specification where t equal to 1 second using this all these values, or we can consider for even capital N or n is equal to 2. So once this n is equal to 2, k equal to, right, to analyze that all, if it is 0, 1, 2, 3, n is even. Okay, with this, so right to measure that all sk value, h into sfn, sn is equal to pi sigma that n by 2, k equal to 1 to n by 2, 1 by s square plus bks plus, we know that's all formula, where bk, if you want to this calculating this bk value, we know that all formula bk value is that bk is like this, where bk is equal to 2 into sine 2 into sine of 2 minus 1 into pi by 2 into 2. It is also equal to 1.4142. Here h into h of Sn is equal to 1 by s square plus 1.414142s plus 1. This is how they are calculating this h of Sn. Coming to this, once we know that n value, order of the filter, n is equal to 2, where k is ready to substitute 0, 1, 2, 3. After trying to decide, n is either even or odd. For this, n is equal to 2, k values, where in terms of n is equal to even, try to substitute the sk is equal to 1 or at pi by 2n plus kn, k pi into n. If the k value right to substitute k equal to that k value is right to substitute k equal to 0. Okay, so here right to use that alias 0 is equal to 1 at pi by 4. Next k equal to 1 where it is followed by s1. S1 is equal to 1 into 3 pi by 4, where that k equal to 2, then to observe this s2 is equal to 1 at 5 pi by 4, where k is ready to substitute that 3, s3, s3 is equal to 1 at 7 pi by 4. Okay, the poles lying on the left half of s plane. So hn of s is equal to, like this, we have to substitute, finalize this particular value. This is the one way. Already we have calculated this one. This is the, or we can use in this all way. User can try to calculate that what you call that h, what you call sk and h of sn value. Of that we try to verify that all graphically. Using this all numerical value and graphically we try to observe this. If it is manual operation or practical operations, once it is the filter design is ready to fulfill using this desirable specifications. Okay, if it is we are meeting that one specification, we need to observe that cutoff frequency omega c is equal to omega s by 10 power minus ks by 10 minus 1 power 1 by 2 pi is also after substituting these all values, where omega c is equal to 2.3562 by 10 power 13.97 and 7 by 10 minus 1 whole power 1 by 4 because of n we know, where after substituting, after finalizing this value, where 1.0664 radians per second. Okay, graphically right to observe this. Okay, the poles lying on the left half of S plane. Unnormalize this transfer function h of s. h of s is equal to h2 of s, s with s by omega c. h2 of s, s stands to what you call s by 1.0644. It is also equal to that 1 by s square by omega c square plus 1.4142 s by omega c plus 1. Like this, we try to simplify this all mathematical analysis. Finally, we try to verify this all, what is the transfer function, how it is varies in typically. Okay, like this. Next example is, so design an analog Butterworth low pass filter to meet the following specification. Using this all specifications are various. Okay, so using this all specified values, this particular specified values with this. Okay, so where omega p or omega s is how it is varies, but it is given design an analog Butterworth low pass filter to meet the following specification. T is specified. Previous example and this example, the T is 1 second, but it is given the task specification. Here it is 0.9 is equal to less than or equal to h into e power j omega less than or equal to 1. For 0 less than or equal to omega less than or equal to 0.35 pi. Here mod h into e power j omega less than or equal to 0.275 for 0.75 pi less than or equal to omega less than or equal to 5. So with this, these are the, by using this all example, based on this all specification, we are to design. How we are designing? What are the given data? Passband edge frequency omega p is given 0.35 radians per second, isn't it? It is assigned according to this that omega p. Okay, stopband edge frequency omega s, where omega s is given here 0.75 radians per second. Passband edge analog frequency omega p is equal to sigma p is equal to omega p by 1 is equal to 0.3 pi by 1. So after substituting this, after finalizing this 0.3 pi radians per second, stop at edge analog frequency omega s is equal to omega s by 1 is equal to 0.75 by 1 is equal to 0.75 radians per second. Okay, like this, try to analyze. So using this all, if go on using the for n value and n is equal to 3 4, how it is varies is you have to follow this all same procedure. Finally we have to measure that all sk value, same similar case. Okay, after trying to verify that all what is all that pulse, how it is reflected, like this. So go on using this type of examples we are going to verify for next. Okay, for and based on this same procedure, you have to follow finding that order of the filter. After that, n value is 4. Try to calculate these all values. Finally, try to verify this analog with Butterworth low pass filter. Okay, this is the example, best example for designing IAR filter using analog Butterworth low pass filter, with the best example in numerical and graphical, with the suitable examples we have discussed with the designing what you call IAR digital filter with the low pass Butterworth filter. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.